forces you see in daily life. You pushing a box, your weight, which is a force acting downwards, hammering a big nail into the ground. All these forces, if you notice, are acting perpendicular to the surface. A force exerted by an object perpendicular to the surface is given a special name. It's called thrust. It's the total force acting perpendicular to the surface. What will be the unit of thrust in the SI system? Can you guess? You should have got this one. Thrust is nothing but force. So the SI unit of thrust will be the same as that of force. Newton. The SI unit of thrust is Newton. What's pressure? Now I don't want the definition or the formula. I want you to understand it. Let me give you a couple of examples. Take a pencil and keep it between your thumb and index finger with the tip touching the index finger and the other end touching the thumb. Now apply equal force from both ends towards the pencil for a few seconds. Release the pencil and observe the two fingers. To be precise, observe the depression you see in the fingers. You'll notice that the depression in your index finger is much more as compared to the depression in your thumb. Why does that happen? Before we answer that, let me give you a second situation. When you stand on loose sand, you see that your feet go deep into the sand. Now, if you lie down on the sand, will you go just as deep into the sand? No, you won't. But if the force exerted in both the cases is the weight of your body, then why is the depth in the first case more? That's where the concept of pressure comes in. Pressure is nothing but the force per unit area. If we're talking about thrust, it would be thrust per unit area. If the thrust is constant and the area is more, then the pressure will be lesser. And if the area is less, then the pressure will be more. Pressure is inversely proportional to the area on which the thrust is applied. Now we can understand the two situations in terms of this formula. What happened in the first situation? As we apply an equal force from both ends, then as per the Newton's third law, the pencil will also apply an equal and opposite force on the fingers. But the depression was more on the index finger. That's because the area on which the tip of the pencil applies a force on is lesser as compared to the area on which the other end of the pencil applies a force on. As the area is lesser, the pressure is more. And that's why the depression is more. Can you understand the second situation using this concept? In the second situation, the area on which your feet lie is lesser as compared to the area on which your entire body lies. And that's why the pressure is more when your feet are on the sand as compared to when your entire body lies on the sand. Which explains why the depth here is more. What is the SI unit of pressure? As it's force over area, it would be Newton per meter squared. This is the SI unit of pressure. And this is also called as Pascal. 1 Pascal is 1 Newton over 1 meter squared. This has been named after a famous scientist called Blaise Pascal who had conducted extensive studies in this area of science. Let's quickly recap what we learned. What's thrust? It's the total force acting perpendicular to the surface. And what's pressure? It's the thrust per unit area. If the same amount of thrust is applied on a lesser area, then the pressure will be more. Say you have a beaker filled with water and you put your index finger inside it. You'll observe that the water level rises slightly. You put in 2 fingers, the water level rises a bit more. And now when you put in your hand up to the wrist level, you'll see that the water level increases significantly. The ancient Greek mathematician Archimedes observed something similar when he got into a bathtub. When he got in, he realized that the level of water went up. In both the cases, you notice that the water is displaced by the object that goes in. Keep this thought in mind. We'll come back to it soon. In our previous videos, We've seen that when an object is placed in or on the fluid exerts a buoyant force on it which acts upwards. The Archimedes principle goes just one step further in saying that the buoyant force applied by the fluid is equal to the weight of the displaced fluid. We can take a simple example to understand this. Take a 5 kg solid object and suspend it by a spring balance. The balance will read 5 kilograms. Let this be the first case. For the second case, take a beaker of water which has a small opening at the top. The water in the beaker is filled right up to this point where the opening is. And we keep a small container under the opening. Now slowly lower the solid object into the water and you'll see that the reading will be lower number as compared to the previous case. Why is that? It's because of the buoyant force acting on the object. You'd have also noticed that some water was displaced. Now in this context, we can say that the weight of this displaced water is equal to the magnitude of the buoyant force acting on the object. That's the Archimedes principle. When an object is immersed fully or partially in a fluid, the upward force applied by the fluid on the object is the same as the weight of the fluid displaced by the object. Where is this principle applied? Can you think of examples? How do you think large steel ships float? It's simple. If the weight of water displaced by the vessel below the keel is equivalent to the vessel's weight, then everything above the keel will remain afloat. That's because the water too applies an upward buoyant force on the ship, which is same as the weight of the water displaced by it. There's just one important concept left in this section, and that's relative density, which we will cover in the next lesson. We've understood what density is. In the same given amount of space, if there are more things, we say that it's denser. Density is simply the measure of how compact the mass in a substance or object is. It's mass per unit volume. And based on this formula, we can say that its unit is kilogram per meter cubed. So can you tell me what relative density is? Look at the word relative. What does it tell you? It tells us that we are looking at the density of something relative to the density of something. We are comparing the density of one thing to the density of another. That's all. But the question is, relative to what? It's most typically the density of water. Yes, we look at the density of an object relative to the density of water. How do we define the relative density of a substance? It equals the ratio of its density to that of water. Yes, density of the substance over the density of water. Can you tell me the unit of relative density? Look at the right-hand side and tell me the unit. As it is a ratio of similar quantities, relative density will have no units. The units from the numerator and denominator cancel each other out. The density of water is 1000 kilograms per meter cubed and the density of silver is 10,500 kilograms per meter cubed. So can you tell me the relative density of silver? It's easy. Just refer to this formula and try answering it. It will equal the density of silver over the density of water. Substituting the values here, we get the answer as 10.5. That's the relative density of silver. What does the relative density tell us though? What can we understand from this? First, it tells us that silver is a lot more dense than water under the given conditions. Approximately 10.5 times denser. But that's pretty obvious given the numbers. This tells us another important thing. It tells us whether the object will float or sink in water. In simple terms, a substance will sink if it's denser than the liquid it's placed in. And it will float if it's less dense than the liquid it's placed in. How can we say this mathematically? If the relative density of a substance is greater than 1, then it will sink. And if it's lesser than 1, it will float. As the relative density of silver is 10.5, which is greater than 1, it will sink in water. But if we take the example of ice, its density is approximately 934 kilograms per meter cubed. So its relative density will be 0.934. As its relative density is lesser than 1, it will float in water. We can understand this with a simple diagram. Take 4 beakers filled with water. In the first one, drop a substance with a relative density of 0.1. You'll see that it floats like this. In the second one, drop a substance with relative density of 0.4 and you'll see that it floats like this. More of it is inside the water. And if it's 0.9, even more of it will be inside the water. But it will still float. And if it's greater than 1, say 1.2 or 1.3, then it will sink. Okay, here's one last question for you. Can the relative density of an object be 0? The answer is no, it can't be 0. Because if the relative density is 0, it will mean that the density of the substance is 0, which in turn will mean that the mass of the substance is 0. For any given substance, its mass in a given volume cannot be 0. And you should also know that relative density is constant only under given conditions. It is pressure and temperature dependent. The same substance can have different relative densities under different pressures or temperatures. Say you're holding a slightly heavy object in your hand. Now, if you try to hold that object within a container full of water, you'll notice that it feels lighter. It doesn't feel heavy at all. What happens when you put an empty glass into a container of water? Of course, the glass fills up with water. So you're holding the glass of water inside the water which is in the container. And now, when you try to take the glass outside the water, what do you notice? Yes, the glass feels heavier when it's outside the fluid. And the same glass full of water felt light when it was placed inside the fluid. And that brings us to the concept of buoyancy. What happens when an object is placed inside a fluid? As we'd seen in the previous video, the fluid pressure increases with depth. Now, because the pressure increases as we go deeper, the force exerted upward due to the pressure will be more than the pressure exerted downwards due to the pressure. So the force exerted on the bottom of the object due to pressure will be more than the force exerted on the top. So this net upward force exerted on objects submerged in fluids is called the buoyant force. You can test this with a tightly closed empty plastic bottle and a container of water. If you drop the bottle on the fluid, you will see that it will float. That's because the fluid is applying an upward force on the bottle. Now hold the bottle and push it inside the fluid. You'd notice that the bottle is also exerting an upward force on your hand. If you leave the bottle, you'll see that the bottle will come up to the surface on its own. I think you can guess why. Now push the bottle deeper inside the fluid. You will feel more force against your hand. And when you release the bottle, it'll rush back to the surface. It'll come up faster than it came up in the previous case. The upward force increases as it's pushed deeper into the fluid. And that's because the pressure also increases as we go deeper into the fluid. This upward force exerted by the water on the bottle is known as upthrust or the buoyant force. Now let's say you simultaneously drop a piece of balsa wood and a metal drawing pin of the same mass into a container filled with water. What do you think will happen? Will both of them float? Or will they both sink? Or one stays afloat and one sinks? We will understand this example in the next video.